Um, Hello, everyone. We are very happy to welcome you today for this webinar on basics of acoustics in underwater applications. My name is Evgenia Kostanaya. I'm the global coordinator for the ECOP program. This is an endorsed UN Ocean Decade program helping early career ocean professionals. This webinar today is the first in our series of webinars related to underwater technology and applications that we are going to develop together with our partners at the Oceanic Engineering Society at IEEE. I would like to introduce our ECOP program's friend and colleague, Hari Vishnu from the Oceanic Engineering Society, who will be your moderator for today. Hari, over to you. Thank you so much for making it happen today.
Thank you, Evgenia. Warm welcome to everybody who is here with us today. My name is Hari Vishnu. I'm a senior research fellow at the National University of Singapore, and I'm also a member of IEEE. Let me say a few brief words about IEEE and how we are connected with the theme of this webinar. So IEEE is the world's largest professional technical organization. It deals with all aspects of electrical and underwater engineering. Oceanic Engineering Society is one of the societies under IEEE, and the ocean being large, naturally, the fields that we are associated with as IEEE, Oceanic Engineering Society, is also large, or OES for short. Now, one of the visions we OES have as part of the UN Ocean Decade is that we want to bring the flavor of technology to the decade. We want to show the effect that technology can have to achieve the aim of the decade, to spread the word of ocean science and to take our ocean awareness to the next level. And as part of that, we are proud to have partnered with the ECOP program. In the past, we've been part of the virtual ECOPS day. We've had a few ECOP conversations. And now this webinar series is starting off very much in that spirit, where we want to spread the word of technology to folks who are interested in using it, in understanding what it's capable of, in just interested what's being done out there. And as you know, there are a lot of technologies out there which we use for sensing, for exploring, for tapping into the oceans. So we, as Oceanic Engineering Society, would like to partner with ECOP program to spread awareness on this. And we have many such webinars planned. We would like to start off with acoustics with Suleman, but we will have many such talks coming for you in the coming months. Now, to start with, we'd like to take a poll just to know where our audience stands with respect to these kind of webinars. So I'm going to start a poll. So it would be great if the folks listening to this could participate. So the questions are basically, have you attended any previous webinars or events related to basics of acoustics? And how would you rate your knowledge level? And while the replies are trickling in, maybe I can introduce our speaker. We have with us today Dr. Suleman Mazhar. He's a professor at Harbin Engineering University, as you can see, and he finished his Ph.D. at Ura Labs in the University of Tokyo, Japan. He finished his postdoctoral research at Georgetown University, Washington, and before he was a former content architect at Educative Axis, that was an edtech startup in Pakistan. As far as IEEE is concerned, Suleman is a very active member of IEEE OES. He is the chair of the Underwater Acoustics Technology Committee. OES has many technology committees catering to various aspects of technology, and Suleman represents a very important one, which is Underwater Acoustics Technology Committee. And here he represents OES in spreading the message of why acoustics is important. Apart from that, he's also the Student Activities Committee. So I'm sure if any of you have questions more about acoustics, you can feel free to reach out to Suleman. So Before we start off, I see that we've got our replies to the poll. So I'm going to end the poll and I'm going to share the results. I hope everybody can see the results. So I see that 76% of the audience have not attended any previous webinars or events related to such talks. So I think that's good that Suleman will be able to spread his message to a community who will be seeing this and learning a lot from this. So over to you, Suleman. Thank you.
Thank you very much, and a very good evening from my side. As Dr. Hari introduced me very kindly, I'm working at Harbin Engineering University and in the Department of Underwater Acoustics. I did my Ph.D. from Tokyo University, postdoc from Georgetown, DC, and then I spent about a decade in Pakistani universities working on marine mammal observation and conservation related projects. I worked with WWF, Pakistan, and ECOP, Nepal, for projects related to environmental monitoring and conservation. I'm also chair for DC Underwater Acoustics. We mainly work on problems and research themes related to underwater acoustics theory and applications. And I really welcome you to join Ocean Engineering Society as well as our technology committee in underwater acoustics. In addition, I also look after student branch chapters in Ocean Engineering Society, which are a great tool to engage youth in ocean and environment related activities around the globe. If you need any information about that, you're also welcome to contact me. So today's talk is basically about basics of acoustics in underwater applications, which is being delivered for early career ocean professionals ECOP decade program. Now let me start with the organization of today's talk. I will share my personal motivation for working in this area, and then I will briefly touch the fundamentals of sound or acoustics. I will discuss how the sound propagates from a medium. Then I will share some examples of underwater sound or noise sources. I will play some audios so that you have an idea about how does it sound underwater. And then I will briefly touch some applications of underwater acoustics. And after that, I'll share some challenges and future directions in this domain. And then we will conclude and we'll open the presentation for question and answers. So, talking about my personal motivation, as I'm from Pakistan. So in Pakistan, there are two very interesting and remarkable things that relate to underwater acoustics. One is the endangered river dolphin, which is famously known as Indus River dolphin or Plantista minor. We are working on the conservation of the Indus River dolphin through scientific study of dolphin behavior and acoustics. It also involves conservation efforts and population surveys. As you can see on the right bottom, there is a person with a dolphin in the hands. So basically what happens during flood seasons is that the dolphin from the main river channels, it moves to the canals. Once it moves to the canals, it becomes very difficult to come back due to the canal flow, and after some time, the canal water level gets low, and with that lower level, there are pockets of water in the canals, and sometimes those pockets get disconnected from the main river channel. As a result of that, there is a high possibility that those stranded dolphins might die in those pockets of water. So there's a program in Pakistan which looks after those stranded dolphins. They use crowdsourcing approach, where anyone who sees the dolphin in their vicinity and near the canals, they report to the wildlife authorities in Pakistan, and then they arrange these missions where they take the vans and cars to that location. They then move the dolphin manually on the vans, which have special equipment and water facility, so that dolphin is minimally disturbed during the movement from the canal to the main river channel. In addition, we also do acoustics-based surveys, and we're also working on developing some transmitters or pingers that may help to discourage the dolphins to enter the canal channels, so that we don't have to face such stranding events. The second motivation is from the Indus Basin system. So Indus River is a very famous river in this region, and it's the largest contiguous irrigation system in the world, this Indus Basin system. And the total length of main canals, branches, and distributaries, it spans over 90,000 kilometers. As you can see on the right side, this is the map of Pakistan, and the blue lines are showing the rivers. And in addition, there are also canals which are shown, which are not shown here. Combining those canal lengths as well as these river lengths, the total length of this basin system is around 90,000 kilometers, and it's the lifeline of Pakistan's economy and agriculture. So we are working on low-cost autonomous monitoring infrastructure to monitor the water quality, because it directly affects the agriculture as well as the marine, the aquatic life living in these rivers. The third motivation comes from my association with IEEE Oceanic Engineering Society, and my research area of underwater acoustic theory and applications. So I use underwater acoustics for different applications, and I actively play a role in different activities of Oceanic Engineering Society. Mainly my work, especially at Harbin Engineering University, is focused on bio-inspired algorithms for conservation and communication. In addition, we use ecological surveys, and we use acoustics in the ecological surveys and marine ecosystem monitoring. So now let's talk about underwater acoustics, but from a perspective that is known to us. Most of us can speak and listen, and we understand a little bit about the speech production process. So this diagram on the right side, you can see it is showing the flow of air. If you keenly observe some lines which are being emanated from the vocal cords on the right side. So the sound from the so air pressure from the lungs passes through the vocal cords or glottis area and passes through this entire region, which is pharynx and oral cavity, the mouth, and the nasal cavity, the nostril and the nose area of the human beings. And by changing this vocal tract, the oral cavity and the nasal cavity, we move our tongue or move our teeth around so that there is a constriction in the path of the airflow which is coming from the lungs. As a result of that, sounds are produced. Right, so the source is the lungs and vocal cord, and the constrictor lies somewhere in the vocal tract, as a result of which the speech is being produced. The same phenomenon is observed whenever a sound is produced in any other medium. A similar phenomenon would be observed. And this sound, once it is produced, it passes through some medium, which can be air, which can be water, and it may even be solid. And based on the material properties of the medium, its properties are changed, and it is eventually perceived as some listening device. For example, in this case, you can see the ear, right? So here you can see on the third diagram below that sound goes into the ear, then it impacts the cochlea in the ear, and then whatever is spoken is perceived by the brain. So this is briefly the steps involved from the production of the speech to the perception of the speech. Now let's look into the equivalents of speech in underwater acoustics. In the underwater acoustics, just like the sound is received by the ears, we have the hydrophones which receive the acoustic signals, and in brain, those acoustic signals are converted by the ears into electric signals or electrochemical signals which are perceived by the brain. But here we change those signals into electrical signals and save that data on the computer. So hydrophones are just like the microphone which is attached to your computer. On the microphone, you speak and the sound is recorded by the microphone and saved on your computer. And similarly, we have the second analogy from the projector or transmitter. Just like the human mouth or vocal tract produces the sound, we have the projector or the transmitter, which converts the electric signal into an acoustic signal. So in vocal tract, there are mechanical disturbances and mechanical movements that play with the airflow coming from the lungs and convert it into the acoustic signal. But here we have the electric signal, which was maybe coming from the hydrophone stored on the computer or synthetically designed electric signal, and we convert it into an acoustic signal using the projector or transmitter. An equivalent example can be seen in the form of the speaker that we attach to the computers. If you have a song file on your computer and you play that file, it will be played on the speaker in the same process that on the computer it's an electrical signal. And when you play it, it changes into an acoustic signal and you can hear it. And both hydrophones and the projectors or the transmitters, they are known as the transducers because they convert, these are the devices that convert energy from one form, which is either electric or acoustic, into the another form, which is again electric or acoustic. So this is the underwater equivalent devices, the hydrophones, projector, the transmitter, which are used for production or the reception of the sound underwater. Here you can see on the bottom some examples of hydrophones here and the projector here. So now with this brief introduction to underwater acoustics, let's look into some historical notes about passive acoustic monitoring. I believe many of you would be knowing about Leonardo da Vinci. In one of the manuscripts in 1490, he actually he wrote that if you cause your ship to stop and place the head of a long tube in the water and place the outer extremity of that tube in your ear, you will hear ships at a great distance from you. So this is I think the first example of a very crude sonar system. Sonar is basically underwater acoustic sound movement or sound ranging. So the first example of underwater acoustic or underwater sound usage is an observation which was made by Leonardo da Vinci. And then, as you know, I believe some of you might have heard about the speed of sound in the air. It's around 330 to 40 meters per second, depending on the properties of different air media at different places. Similarly, there is a speed of sound in underwater environment, and in 1827, the speed of sound was measured in Lake Geneva by Charles Francois. And on the bottom right, you can see the setup which was used to measure this speed of sound. So, as you know, there's a formula about the speed, velocity, or speed is given by the distance over time, right? So using this infrastructure, so there are two parts of this infrastructure. One is the light source. So the people on this ship would play a light, and at the same time, when they play the light, they produce a sound using some bell underwater, and that sound will travel underwater from here to the second ship. And there will be someone, observer here on this ship, who will look at the light the moment he sees the light, he starts his stopwatch or his time measurement. And as soon as he listens to the arrival of the sound here, he stops his stopwatch or the time measurement device. And based on that, he gets the total time required for the sound to move from this ship to this ship, right? And this time, when put in denominator, and this distance x, which is written here, when put on the numerator, will give you the speed of sound. So that was the first ever measurement of the speed of sound that happened in 1827. And it's a very basic experiment, very easy experiment that even you can very easily do in any environment around you. And you can actually find that the speed of sound is around 1500 meters per second, which is roughly about 4.5 to 5 times more than the speed of sound in the air. Right. Okay. So let's move ahead. So here you can see another example. So in most of you might have heard about Titanic, right? In just after the Titanic event, Richardson he suggested using the echoes for ranging and detecting icebergs. And based on that suggestion, in 1914,
I think Suleman is having a connection problem temporarily. Let's just wait for him to. Hi, Suleman.
Hello.
Okay, we can hear
Yeah.
you now. Yeah.
Okay,
While you're
great.
at it, your equations are still on the screen. Would you be able to clear that before moving on?
Yeah, that's why I'm actually sorting out where to clear it from. Annotation. Okay, I got that. Clear all rights. Yeah, that's right. Sure. Thank you. And right. So we were talking about that Titanic event that happened due to a hidden iceberg. And based on that, after that event, people were looking into the ways to, get rid of such problems. And Richardson, he suggested using echoes for ranging and detecting icebergs in 1912. And then there was a moving coil transducer, some sort of an underwater projector, which was proposed in 1914. And so it was used to monitor the presence of icebergs or disturbances or some targets underwater using this particular transducer, using the underwater echo. So the sound would be produced from this device. It will hit the iceberg if it is in front of the sound, this projector, and will come back and record it by the projector. Based on the time that is taken in this to and fro motion from the projector to the iceberg, the system attached to the projector can help you to identify how far is the obstacle or the iceberg underwater, and can help you to avoid accidents. Right. So now with this historical and brief introduction about sound underwater, let's look into some fundamentals of sound. So what is sound actually? Briefly speaking, it's the fluctuation of air or the medium pressure which is carried through the medium. So there are some prerequisites, as we just saw. You need to have some source of energy. Either it can be the pressure of the air coming from the lungs, or it can be the mechanical disturbance produced on the projector that is going to disturb the medium of air or the medium of water. And then this source of energy is produced by a vibrating source, which can be, for example, a tuning fork or a piezo ceramic disc. It's the material which is used to make microphones or the underwater projectors or hydrophones. And then we need to have a medium of transmission, which is air or water or any maybe solid material. And then, so for production of sound, most probably we don't need the receiver. But obviously, so there is a saying that goes that if a tree falls in the forest and there is no one to hear it, so does it make a sound, right? So the receiver is also important if you want to do some processing of that sound. Now, we have talked about the mechanical or the physical aspect of the sound, but mathematically or on our computers or from the physics point of view, we represent this physical aspect of the sound with the help of some waves. So for every physical disturbance that sound produces in the air, we normally represent it in the forms of the waves which are being shown in front of you here. So this is a sound wave, as you can see here. And this, so this is a typical sinusoidal wave. If I talk in mathematical terms, a sine wave. So if you plot a graph of sine theta t as a function of time, so it will be just like this graph. And such graphs or such sinusoidal waves are produced by many physical phenomena in the nature. One example is a tuning fork. I believe many of you would have seen this device. It's a metallic device. You struck it on some plate or some solid body, then the forks of the tuning fork, they start vibrating. And the way they vibrate is that they are going to create compression of the air and the rarefaction in the air based on their physical mechanical movement, which is usually to and fro. So these forks, they are going to move like this and like this. So they will be moving like this in this fashion, right? So when they go, when they move this direction, so they are going to pressurize all the particles of the medium together here. And when they go this direction, they are going to relax all the particles of the medium in this manner. As a result of this, what happens is that we can represent this operation in the graphical form like this, that we have whenever there is a compression in the medium, we are going to represent it as a high amplitude wave like this. So the maximum pressure is at a point where there is the maximum amplitude of the sinusoidal wave. And the lowest pressure corresponds to the negative highest point of this sinusoidal wave, as you can see. So in this manner, we can plot it. So here you can see this rarefaction is the minimum pressure, and this compression is the maximum pressure of in the medium. And as a function of time, we can plot like this. So this amplitude represents actually the displacement of the particle motion. And we call this graph the particle motion graph as a function of time. But at the same time, if you look at this positioning of the particles of the medium, we can also draw a graph in space. So let's assume that all these particles are plotted at a time t is equal to, let's say, 10 seconds, right? So at 10 seconds, if this entire space represents an axis, let's say call it x. So this is the space axis as shown here. And if we plot this, or if we represent the maximal compressed area as the maximum point of this curve and the maximum relaxed area as the minimal point of this curve, we can again get a sinusoidal wave. So as a result of this movement of the tuning fork, we can see that we get a sinusoidal wave both in time as well as in space. So this is the space around the tuning fork. So here you can also see that light color is representing at a particular time 0 or particular time t is equal to 1, it is representing the areas of compression and rarefaction. So here, basically what we are seeing is a sort of a sinusoidal wave, if you know, like this. So this is the sinusoidal wave in space. But if you just observe a particular point here, so this particular point, which is in the vicinity of this tuning fork, it will be vibrating as well. So it will go maximal here and maximal in this direction. So based in, and if you just look at this particle in time, then again you can draw the trajectory of this particle as a function of time, and you are going to get this sinusoidal wave like this. Because first of all, it will have zero displacement when there is no sound. Then slowly, as the mechanical disturbance arrives at this particle, it will start moving away from its central position, and it will reach some maxima. And when the source of this disturbance, that is the movement of the tuning fork, it goes back to the other direction, it will start getting relaxed and come to the 0 point, and then it will become rarefaction. So it will become more relaxed and go to the negative cycle. So it will be a sinusoidal wave, essentially. Now, this amplitude of displacement is also known as the intensity or power of the sound. Right. So now there is another thing which is so the sounds are, or the waves are of two types actually. They are like transverse waves and the longitudinal waves. So the transverse waves are those waves in which particles of the medium, they move perpendicular to the movement of energy. So for example, if you pluck a rope which is connected to some wall and you move your hand up and down, so the particles of the medium, which is essentially a rope, those particles are moving up and down, but the energy is moving in the forward direction, and it's making a sinusoidal wave in space, and it is actually hitting or putting a pressure or a force on the wall. Similarly, if you have a spring and you just move it back and forth by picking it at the other end, and the second end of the that spring is attached to a wall or a support, and if you just push it back and forth, what we are creating is a longitudinal wave, because here the particle of the medium are moving back and forth in parallel with the movement of the energy. So do you have any idea what type of wave is the sound wave, by the way? I mean, if you just think about this analogy here, the particles, they are moving back and forth with the direction of the sound. So clearly, as the sound particles are moving back and forth parallel to the movement of the energy, so the sound waves are essentially the longitudinal waves. Now, looking at the graphical representation of the sound, we define some mathematical properties, some physical or mathematical properties, which we call, like, there are three essential parameters of a sound. One is the wavelength, and this is basically for a particular wave. It is measured from the crust to crust or from the trough to trough. So we call this as the wavelength. So this is basically essentially the length of one single wave on this particular sound wave. So as you can see that one sinusoidal wave, one full sinusoidal wave circle is completed from one trough to another trough, or one crust to another crust. So this is known as the wavelength, and it is measured in meters, or more specifically in centimeters or micrometers, depending on how high frequency sound is it. Second thing, as we already discussed, that all waves, whether sound or the light wave, they have a speed. The speed of sound in the air is 340 meters per second, approximately. And similarly, we have another quantity which is known as frequency, which is the number of cycles, or the number of occurring of this wave per second from a particular point in space. So it's, in other words, it's the number of cycles per second of this sinusoidal periodic wave. And we measure it in hertz, which is cycles per second. And there is a notion which is called time period, which is again related to the frequency, and time period is just simply the inverse of frequency. Did anyone ask any question? Okay. So these three entities are related to each other. So the product of wavelength and frequency is equivalent to the speed of sound. I won't be going into the mathematics of this, but we'll just keep record of it for our further discussion without going into the tough maths. The second thing about sound is the sound intensity or sound amplitude. We normally measure the sound energy in decibels. You might have heard this word a lot, especially if you're visited to a doctor who looks into the ear. They normally also talk in terms of decibels. So any sound intensity, which is normally measured in watt per meter square, can be converted into decibels by using this formula, which is 10 times log of I, where I is the intensity, sound intensity of our interest, and we divide it by some reference threshold power intensity, which is for the case of the sound in air is 10 raised to power minus 12 watt per meter square. And this sound level in intensity is equivalent to the properties in power. So 20 log of power or the pressure divided by P naught. So P here is the pressure, and P naught is the reference pressure, which is the threshold pressure, which is 2 into 10 raised to power minus 5 Newton per meter square. And it gives us the same sound level, because intensity and power are related by I is equal to P squared. So it's the quadratic relationship between two entities. So now actually let's look into what does it actually mean. So if we have a sound of 60 dB, it essentially means that the intensity of the sound was about 10 raised to power minus 6 watt per meter square. And this intensity is about 0.000002 atmospheric pressure. And this is actually, the atmospheric pressure is very high pressure, and this 60 dB sound represents the conversation, the daily conversation that we have between the humans. And it's quite lighter than the atmospheric pressure. Then there is 120 dB sound, which is the brain threshold. If somebody speaks very loudly near you, and it reaches about 120 dB, this is around 1 watt per meter square. And this is about 0.002 atmospheric pressure. So essentially, even the brain threshold is lesser than the atmospheric pressure, which we observe on our body on this earth. And then there's a 10 dB sound, which is barely detectable sound. Just like if you talk to someone in his ear, no one else would be able to hear that sound. So this is barely detectable sound, and it's a 10 dB sound. So this brings up a question here that why don't we feel pain in that, in the atmosphere when the atmospheric pressure is much higher than the conversation and pain threshold? Any idea? Because pain threshold is about 20 Newton per meter square, and atmospheric pressure is far more than that. So answer to that question is that because, so the atmospheric pressure is applying on our body, but there's also sort of, the way our body has been developed is such that we have an internal pressure in the body, which minuses that atmospheric pressure, and the net pressure on the body is essentially zero. Actually, we have an internal body pressure, which negates the atmospheric pressure. Otherwise, if that pressure is not there, we can, the body can even burst. That would be such a painful experience. And there are some very interesting facts. I'll go through these facts a bit quickly because there are a little more chunk of material that I have to cover, and we are already at 7:40. So the pressure that we receive on our ear, those pressure variations, they displace the membrane or the eardrum or the microphone. And as a result of that pressure variations, we measure the sound. Human voice moves the eardrum or the microphone's PZT element by a very small distance, which is about 150 nanometer. It is 1/4 wavelength of visible light. And threshold, if you are speaking at a threshold of hearing, like that is at a very low sound, that would be around 5 × 10⁻⁻8 millimeter motion of the eardrum. It is 1/2 the diameter of a single atom, which when disturbs your ear, you can hear a very like low power sound. And the pain threshold, it creates a displacement of about 0.05 millimeter in the eardrum. Now there is another thing. This is about the power. There is another thing which is about the frequency. The frequency is actually the rate of change. So our ear, it ignores the changes which are slower than 20 hertz. So if our eardrum is moved less than 20 times per second, it's a 20 hertz, and our ear won't note this change. So for example, if you climb the chairs, the air pressure would change, but that air pressure change as you go upstairs would be too slow to be perceived as a sound by your ear. Similarly, eardrum cannot perceive a sound which is greater than 20 kilohertz. Like it cannot, this eardrum membrane cannot wiggle so fast, right? So now there is I want to share some demonstration that compares sound waves in the water and the air. One thing is that, when we are taking these measurements in decibels here you can see the sound level in decibel that we are calculating. So here there is I0 or P0. These I0 and P0 values for air are different from the water. So this is just a convention. We could have decided some other convention, but by convention, in air we are using 20 micropascal as the reference sound. So in air, the reason we are taking this 20 micropascal as a reference sound is that this is the power of the minimal sound that the ear can perceive. So for example, the sound of a mosquito would be around 20 micropascal. As far as water reference is considered, it is 1 micropascal, and this is more a generic selection that 1 micropascal is has been taken as a source of reference for the underwater applications. And so one thing is that intensity of the sound as perceived in water or in air, it depends on the wave pressure, which is measured in decibels or in Newton per meter square. The second thing that affects the medium dense, the intensity of the sound is the medium density. The more dense medium, we are going to observe more powerful sound, and similarly, the sound speed in the medium. So let me share a demonstration now. So right. Okay, just a second. So
sound waves in water and sound waves in air behave differently because of the physical differences between air and water. The intensity of a sound wave depends not only on the pressure of the wave, but also the density and sound speed of the medium through which the sound is traveling. Sounds in water and sounds in air that have the same pressures have very different intensities because the density of water is about 800 times greater than the density of air. Sound levels given in decibels in water are not the same as sound levels given in decibels in air.
right. So here you can see this demonstration. The above source or the circles are showing the sound wave in the air, and the lower area is showing the sound waves in the water. Here you can see that as we produce the sound simultaneously from both sources,
Sound because of the physical difference.
We can see that the circle which is being produced by the source underwater is quite big one, and it is moving quite faster away from the source. So this dot is the source of the sound, both above and below. The reason is that underwater sounds, the speed of the underwater sound is quicker. Its speed is about 1500 meters per second, whereas the speed of the sound in air is about 340 meters per second. It's a difference of about 4.5 times. So sound moves very quickly underwater, and there is less absorption of power in the medium. And the second thing is that the density of the medium, it helps more in underwater environment. So the sound wave can travel a longer distance due to the very dense environment. So as a result of that, the sound wave is a very good tool for communication underwater as well, because the sound wave which is produced in the air cannot go very long distance. So for example, if you look at your mobile phones, although it's an acoustic device, but behind the scene, it is using electromagnetic waves. So acoustic energy is converted into electrical energy, electromagnetic energy, and is then transmitted as an electromagnetic signals from the tower of the mobile company to some other tower, and from that tower of the mobile company, it is received on the mobile of your friend, that electric signal, and then that mobile converts that electric signal into an acoustic signal. So in air, we cannot use a device to produce a sound that can go for a longer distance. And even if we produce, a device that send a sound very longer distance, it will have to produce a very high energy sound, which will disturb all the other people around. So in electromagnetic signal in the mobile phones, we can get rid of that problem. But in underwater, electromagnetic waves are a failure because they don't go very large. They don't go for a larger distance. And acoustic waves come handy underwater for communication as well. So this is one interesting thing that I wanted to share with you. And now let's get back to the original flow of the talk.
Differences between air and water.
Right.
The intensity of a sound wave depends not only on the pressure of the wave, but also the density and
so here we go back. Okay. So one thing was the comparison of the sound in air and the water. And then the second thing is the comparison of different sounds which are produced in air and water. So here you can see in this graph, so there are two graphs here. One is the graph on the left side, which is showing the sounds which are produced underwater. And in this graph, you can see there is there are two axes here. One is the x-axis here, which is the frequency axis. Here is the frequency, right? The frequency is going from 1 hertz up to 100,000 hertz. And there, and on the y-axis, you have the power or the spectrum level. We call it spectrum level, but it's sort of an amplitude. So amplitude of a particular frequency. And there are different lines which are showing different sources underwater. So for example, the black line here, right, here and here, it is showing the limits of prevailing noise underwater. So most of the sounds which are underwater, they lie in this region in terms of frequency and energy. And the red line, which is here, it is representing the heavy traffic noise from the shipping. And the light line here, it is representing the precipitation noise. So these are the frequency ranges in which these sounds are present, and these are the power ranges on the y-axis, which represent these sounds. And similarly, there are many other sources underwater, and you can see those sources shown here. And for example, the oceanic traffic zone or the bubble zone due to surface agitation or surface waves, they occupy different frequency ranges and powers. If you compare it to the sounds in the air, we can see that in air, we don't have the frequency graph here, but we have the decibel or the power graph. The jet craft sound is about 140 decibel, whereas the maximum power sound, which is due to the earthquakes or explosion in underwater, is about 140 dB. Similarly, a typical, the pain threshold starts from 120 dB. And similarly, the rock concert has a noise level of about 100 dB, and then whisper is about 40 to 30 dB on this graph. Whereas 40 to 30 dB is a very low sound underwater. So these are some practical values in decibel about sound waves in underwater and in air. So now let's move ahead. So there is another thing which is very interesting, which is a function of both the speed of sound underwater and the frequency content of the sound in water and air. So you know about bats and dolphins. The bats use sonar system in air for echolocation, for navigation, to find their to capture their prey. And same role is used by the sound for dolphin in underwater environment. Just because of the fact that there are some minor changes in the properties of sound in underwater and in air, both animals, they adjust their acoustic systems according to the properties of transmission media. So because in underwater, it's more dense and the speed of sound is higher. In air, it's a rarer medium, it's a low speed medium. So bats uses around 30 to 80 kilohertz in their sonar system. They produce sounds of 30 to 80,000 hertz, whereas toothed whales, they produce sounds up to 200 kilohertz, which is around, by a factor of 3 to 4 times the original sound of the bat. And the reason is that this frequency of, for example, the 80 kilohertz used by the bat, it gives some spatial resolution. By spatial resolution, I mean that how small object a bat can identify using its sound signal. So the limit of spatial resolution is roughly given by the size of the wavelength used. So for this frequency, the size of the wavelength for 80 kilohertz can be given as about 4.3 millimeter. And with 4.3 millimeter, bats can echolocate objects of few millimeter size, like insects. In underwater, 80 kilohertz would give a bigger value in terms of millimeter. It will be a low spatial resolution. Therefore, the toothed whales increase their sound frequency up to 200 kilohertz. So high frequency means a lower wavelength. So as a result of that, they get a spatial resolution which is matching to that of bat if they use a signal of 200 kilohertz. So this is one interesting fact. Just due to the difference of the sound properties in both media, bats and dolphins, they use different frequencies in order to use the sound for navigation as well as for prey capturing. Now we come to a little bit of mathematical and theoretical discussion. So every sound, so far we have seen sinusoidal sound, as you can see here on the left side. So here you can see that this is a sound. Let's assume this is a sound that has 100 cycles per second. So we define some mathematical analysis, which we call the frequency analysis or the Fourier analysis. And we say that a frequency of 100 would be represented on the frequency scale by a bar at the point of 100 hertz. So for this wave, which is about, there are 100 waves per second, it will have a single bar at 100, and the amplitude of that bar would be equivalent to the maximum amplitude in the time domain. So this is the frequency graph of the frequency analysis of this time domain sound wave. So in the frequency domain, we are going to get just a single spike at 100 hertz, whose height would be equal to the amplitude of the time domain wave. Similarly, if the height of the time domain wave is a bigger one, so you get a bigger spike here. Now, in actual life, both in underwater and in air, we get far complex tones. And all those complex tones like this, they can be decomposed into component frequencies. So if, for example, if you do the Fourier analysis, you will see that, for example, this wave would have two frequencies, two sinusoidal frequencies. One would be at 100 hertz, the second would be at 200 hertz. Similarly, this frequency, which is slightly more complex, would have a bar at 200 hertz and the second bar at a 400 hertz. So just like a sound that you produce from your mouth, like ah, ee, oo, these are complex sounds and they contain many frequencies, like 200 hertz, maybe 1000 hertz, like that. And all those frequencies are very intelligently discerned by our ear canal, which is in the ear. So this is one structure, the basilar membrane in the ear, that converts the time domain signal that enters our ear into a frequency domain representation. So this time domain signal makes this ear canal vibrate at those frequencies which are component of this time domain signal. So for example, if this time domain wave enters the ear, we will have a disturbance at about 200 hertz, like here, whose intensity would be equivalent to this, and the second disturbance would be here, like at 400 hertz, and rest of the membrane will not vibrate. And there would be neurons attached with these this basilar membrane. Those neurons would tell the brain that, look, there is a sound that has a frequency of 400 hertz and a frequency of 200 hertz. And brain would know that maybe it's a sound of ah, ee, oo, or any human-like sounds or any non-human-like sound. So interestingly, our brain does the frequency analysis automatically, and we do it mathematically on computers. So similarly, one square wave, as you can see on the top right corner here, it can be approximated by an infinite number of sinusoidal waves. So you can have infinite number of lines in a frequency domain signal here for a square wave. Right. So now that you have got the idea of time domain signal as well as its frequency domain representation, I can tell you a little bit about hydrophone specification. Hydrophone, if you recall, is the same device, or the projector is the same device as your microphone or the speaker in the real world on the computers. So those microphones or hydrophones, they are represented by their frequency response and their directionality. So the curve that you see on the right side here, this curve is a frequency curve, and it is telling on the y-axis is the dB relative 1 volt micropascal. Relative 1 volt micropascal means that it's the underwater sound that we are looking at, because in underwater we use this 1 micropascal reference. So dB is the power of the or the pressure, and here we can see that the pressure of so this is the receiving response of a hydrophone. That hydrophone receives all the frequencies from 2 kilohertz up to 38 kilohertz equally well, slightly equally well. So it has a hydrophone would have a higher response at this point, but here also it has an approximately good response. And as you increase the frequency, the hydrophone would produce less power also. So normally we define our devices with the help of such graphs, which are known as the frequency response. The second thing is the directivity or the directionality. Most of the microphones or the hydrophones that we use, we call them as the omnidirectional sensors. By omnidirectional, we mean that in 360 degrees, like starting from the 0 degree up to entire this circle, they produce almost same response to the input signal. Any input sound, for example, at 18 kilohertz with, let's say, 10 dB would be perceived as 10 dB for all angles, like whether the sound is coming from this direction or it is coming from this direction or it is coming from the right direction. the hydrophone or the microphone is giving the same response or same output of energy. But there are many hydrophones or microphones which are very directional. They just listen to a sound from a particular direction. So for example, this graph is showing a directional hydrophone, which has a different response on the back side and a higher response on the 0 degree. This is another hydrophone or a projector, which has a high response on the vertical direction and lower response in the backward or the horizontal direction. So we can have directional hydrophones as well as omnidirectional hydrophones, and both could have different purposes. So normally we prefer to have directional hydrophones when we want to avoid noise like situations and we want to listen in a particular direction. But in most of the cases, like for dolphin surveys, we use omnidirectional hydrophones. Right. So here are different underwater sound noise. So right now, I think we have a lesser time, so I won't play all these sounds, but I will just play one sound underwater, which is that of the humpback whale. So let me share the screen here. And let me see if here we have the humpback whale. So this is one typical sound which is produced underwater, and it's a whale sound. And you might have heard humpback whales if you happen to live near the coastal areas where these whales are found. And there are many other links that you can actually use. And so this is basically all these sounds are coming from docits.org, which is a project on underwater sound. And let's so this is a biological sound which was coming from a whale. Similarly, we can have anthropogenic sources, some noises that are man-made, and let's have one example from the man-made sounds as well. So let's have some man-made. So here is a sonar system that we produce underwater for submarines or ships. So let's listen to this sound. So here you can see, so this sonar system is just like a tone of a sound. It's just like a tonal sound. Like it has a particular frequency at which it is playing the sound. And so these man-made sounds, actually, they impact the normal operation of the marine mammals as well, the biological sources as well. Lastly, I will talk about some interesting sound properties underwater. So here we have a graph which is telling us the role of different water parameters. Like so, in water there is pressure, there is water has a temperature, as well as water has a salinity. So with as the depth of the water increases, the salinity of water decreases, and similarly, as the pressure at the depth decreases, depth, we go further deep in ocean, the pressure would increase. Similarly, if you go deeper in ocean, the temperature would decrease. Now, the thing is that with the variation of salinity, pressure, and temperature, there is a change in the speed of sound as well. For example, so this is on the right-hand side, there is a graph which shows you the speed of sound underwater at different water depths. So on the x-axis, you can see here is the x-axis. It is telling you the speed of the sound, which is 1480 or 1500 or 1520 meters per second. At the surface level, which is near this depth, the speed of the sound due to particular profile of salinity, pressure, and temperature, this speed of sound is around 1510. As we go down, the temperature of water gets lower, and with lower temperature, the speed of sound also gets lower. So, and then as you go further deep down, we have a deep isothermal layer where temperature becomes almost constant, and there are other parameters like the pressure and the salinity, which are going to decide the speed of sound. So this is a particular sound, we call it sound speed profile at different depths. The reason I'm showing you this sound speed profile is that, you know, it results in a very interesting phenomenon when we produce a sound at different levels of depth. For that to see, so here is one thing. So as you go deep, as the sound is lazy, it tends to bend towards the region of slower sound speed. So for example, if you have an environment like this, you're going deep and water is colder in depth, the sound would bend towards lesser temperature, which is slower sound speed region. Similarly, if you have an environment like this, where you have a warmer water down and cooler water up, the sound waves would bend towards upside. Now this has a particular impact on propagation of sound underwater. You might know about Snell's law about waves for the optical waves, that when some wave strikes the surface, part of the wave passes through the medium, it is refracted into the medium, and part of the wave is reflected back. So that's the Snell law. There is another property, which is total internal reflection property of sound as well as other waves. At a particular, like 90-degree angle, most of the sound part would be reflected completely. But as the angle of incidence increases, for example, in this diagram, you can see this is the 90-degree strike. Most of the power of the wave is reflected back. However, if this wave strikes at a larger angle, there is some critical angle, we call a critical angle, at which when this wave strikes the surface or the bottom, the wave is totally reflected back into the medium. Like it goes like this. It doesn't go inside here. It doesn't go here, right? So these two laws, the Snell law as well as the properties of sound underwater, they result in a very interesting phenomenon, which we call the SOFAR phenomenon. Like at a particular depth underwater, when we produce a sound signal, due to the particular properties of underwater sound as well as the Snell law, the sound tends to travel in a very narrow channel, deep sound channel. And normally this phenomenon is used by many animals as well as by submarines to get themselves obscure from the enemy sensors. So this is very interesting property that we observe underwater. Right. So now I'm going to talk about some. So then there is, since we use the hydrophones to detect the sounds, so detection of any animal or any submarine, or if we are using some projector to find an iceberg underwater, the detection of that iceberg is normally dependent on some mathematical parts of that sound, which are represented by these equations. So due to the time factor, I won't be explaining it much, but just to talk about briefly, we have the source level, SL, which is coming due to the, so for example, let's think that we have a hydrophone here, right, which is attached to this board, and it is trying to listen to the sounds from the dolphins. So whether the dolphins are detected by our hydrophone or not, it is dependent on this mathematical equation. This mathematical equation is telling that what is this, we should have some source level. So source level is the energy coming from this animal. The energy of the sound coming from this animal, that is the source level SL, you can see here, right? So this energy will travel up to the hydrophone here. When it travels up to the hydrophone, some part of the energy would be lost at the transmission loss. As the sound goes from here to here, some energy would be lost, and we can mathematically calculate that loss. I'm not going to show that equation here, but you can find it in the references on this website. So transmission level has to be minused from source level. Then there will be some noise level in the vicinity of this dolphin as well as the hydrophone, that noise level would have to be minus. And then there is something which is known as the directivity index. I talked about the directivity index of the sensor. So if this sensor is a directional sensor, it will add, so this minus minus would become a plus here, so it will add positively. But if it is an omnidirectional sensor, it would have tend to a constant directivity index, so it won't help us much. So as a result of that, we'll get a sound signal which is DT, which is the direction threshold. So we compare this sound signal with the detection threshold of the sensor. If the signal coming from this part of the equation is higher than the detection threshold, we can listen to the dolphin. Otherwise, we cannot listen to the dolphin. A similar equation is applicable for man-made sonar system, whose source is showing here. So in this case, the sound would go here. First it go here and then it comes back. So there would be that twice of transmission loss because we are passing two paths. So as a result of that, we have almost the same equation, but with a -2 here. So if again the signal which is received at the sensor here is greater than the threshold of the sensor, we can detect the iceberg, otherwise no. Right. So this is the basic sonar equation, which is very commonly used by the scientists in sonar systems. Now I'm going to talk very briefly about the application of the underwater acoustics. So underwater acoustics is used for underwater positioning. For example, on your right hand side, you can see that here is a ship. It sends the sound down, and if there is a fish here, the sound will strike here and it will go back, and the ship can detect whether there's a a school of fish or not. So similarly, you can do the animal tracking, and similarly, these ships can use the sonars for navigation, but instead of detecting a fish underwater, they are focusing on some iceberg or some obstacle. Similarly, security reasons we can use, and for seabed mapping, for AUV service, we can use sonar systems. And there are different mathematical methods. I'm just writing those names. I won't be going into the details, like received signal strength indicator, angle of arrival, trial iteration using TDOA, which is time difference of arrival. We use all these methods for positioning, tracking, or localization of a sound source underwater. So this one was, positioning, detection, and localization that we can do underwater. Similarly, we can use sound for underwater communication. So between if there are divers underwater, they can communicate with the mothership using underwater communication system, the sounds. Submarines can communicate to each other and the mothership with the autonomous underwater vehicles using sounds. Data can be collected from underwater buoys and underwater networks. For example, oil and gas exploration networks, they tend to have many sensors underwater, which acoustically transmit the data from underwater infrastructure to the buoy which is floating on the sea, or to some mothership. Similarly, wind tunnels and infrastructures which are deployed in the sea, they can be monitored using the similar equipment or networks. Similarly, there is a noise impact due to the man-made noise underwater. We are facing a very high level of underwater noise pollution, which is impacting the dolphins and whales. The sound is impacting the way these cetaceans they do foraging or their diving behaviors. Their navigation is impacted by the human sound and noise sources like the shipping noise or the oil and gas exploration noise. Similarly, there is one big problem these days is the plastic pollution or debris pollution underwater. We can use side scan sonars underwater to monitor underwater pollution. These are some of the statistics from one Japanese ship, which is they explored the Western North Pacific, South Pacific, Atlantic, and Indian Ocean, and they found that the plastic and debris was found at different depths. And this is very alarming if you look at it. The maximum depth of the plastic was observed to be about 10,000 meters. and the higher deepest point underwater is about 11,000 or maybe less than 12,000 meters, if I correctly remember. So the plastic that we are producing is going as deep as the depth of the sea. So we can use sonar systems to monitor the plastic presence underwater. And similarly, so now some of the challenges and future directions, we can use underwater acoustic for environmental conservation and ecological monitoring, for noise pollution, it's measuring noise pollution and its impact. Similarly, there are many underwater to air communication applications nowadays for finding missing planes, ocean scientific exploration, submarine, airplane communication. We can do those type of exploration. These are some active areas, and that brings us to the conclusion of this talk. And if you have any questions, you can ask now. And I have also shared my email addresses and my webpage of the university. You can reach me there. And also, if you have any questions related to student branch chapters or underwater acoustics, technology committee of Oceanic Engineering Society, you can contact me by email as well as the questions here. Thank you. Over to you, Hari, and I'm really sorry. I think I took a lot of time. Apologies for that.
No worries. Thank you for that extensive talk on acoustics basics, Suleman. So if anybody has questions, please ask them here. Meanwhile, we would like to have your feedback on how satisfied you are. So I'm just going to launch that poll. So please give your feedback on whether this met your expectations and whether you would like similar talks, maybe focusing more on the application. So Suleman briefly touched on this topic towards the end, and you got a rough idea of the fact that acoustics can be used in many applications. I myself am an acoustician and I use it for climate change studies, for example, but you can use it for marine mammal monitoring. You can use it for defense, for I don't know, detecting submarines or mines or things like that. You can use it for studying the ocean. So would you like more talks on such topics? Would you want to know how it can help your careers? So please give us your feedback on these sort of topics. And if anybody has questions, feel free to type them into the chat window here. Okay, we have a question from Morgan Ray. She is looking for a group currently collecting data on ecosystems in the Atlantic Ocean using sound. So Suleman, are you aware of any such groups directly?
So no, directly I'm not aware of any particular group, but so we for example, Oceanic Engineering Society and myself, we are working with Schmidt Oceanographic Institute, and they have like a 10-year program for ocean monitoring, by the way. And this is one of the group which is like an NGO, and they provide resources for students. You can join for free. Also, we have one collaboration with Schmidt Oceanographic Institute. I just write the name here as well for your reference. So we are doing a collaboration with Schmidt Oceanographic. Sorry for misspelling.
Yeah, I've pinged the link in the group in the chat anyway. Yeah.
So this is the name of the institute as well, and you can contact IEEE OES as well, because we are also working on a program which is in collaboration with SOI, with Oceanographic Institute, planning to fund students and young professionals, and those actually that program will cover. One part of that program would be actually into the Atlantic as well, Atlantic Ocean as well.
I can add on some more things. So Morgan, your question is fairly general. So if you're looking about how sound can be used to collect data on ecosystems, one way of doing that is marine mammal monitoring, right? And there are a lot of groups doing marine mammal monitoring in all oceans around the world. The Atlantic is no exception. And a lot of groups in the US, UK, and in Europe doing that. So would you want links to some groups doing that? I can just point you to some universities and labs doing that, and they perhaps have resources that you're looking for. Okay, I will ping that here in a moment. So University of St. Andrews is very active in marine mammal acoustics, by the way. And if you look at their bioacoustics program, it is pretty strong. And I know that they have an active group with a lot of students focusing on marine mammals in the Atlantic. So let me ping that here first. Sorry, Suleman, you were saying something?
Yeah. So actually, yeah, I mean, University of St. Andrew actually is very, they have a very vibrant group which is working on marine mammal, not just acoustics, but also many other areas as well. In fact, in Pakistan also, we are doing some experiments. We did some experiments with industrial dolphin with one of the researchers from there. She worked on tagging of the dolphins and then monitoring the dolphin behavior as well as paths in the river. And also, I think for if you're talking about underwater acoustics groups, you can find many in USA. There is Scripps Oceanographic Institute. Then there's the Woods Hole Oceanographic Institute. So I write their Scripps Oceanographic Institute. If I correctly remember, it is with University of California, San Diego. And then there is Woods Hole Oceanographic Institute, which is in near Boston. They normally work with MIT. And then there are many other, like University of Rhode Island, also in United States has a group working in this direction. And then there are many other countries as well. For example, in Pakistan, we have a small community, and then in China as well.
So we have another question. Sorry.
Yeah. So there are actually two questions. So one question was about, I think, from Nithya. She asked, so they asked that how to start building our career in marine bioacoustics. Actually, there are many different areas from which you can enter into marine bioacoustics. I did my bachelor's in computer science, by the way. And then I worked a little bit in acoustics. And then I get in, I worked on speech processing, by the way, during my bachelor's. And then I entered underwater acoustics during my Ph.D. So you can come from a computing background. You can even come from linguistics background, by the way, if you want. The thing is that you will need something, first thing would be acoustics training, and the second would be biological training and the opportunities. Those opportunities are mostly there. For example, if you get in touch with the local wildlife groups, there are most of the times there are wildlife authorities who are looking after sea resources in the ocean or even the rivers. And then, so for example, if you're coming from the biological background, you need to learn a little bit about the acoustics. And for that, maybe you can take some coursework online related to acoustics, and there are books as well that you can go through. If you read about a little bit about the speech processing, that can help you understand acoustics better. This is one thing. So these are different, and if you're coming from the electrical or computer science background, most probably you'll have to talk to the people in the biology or the environmental department. So you have to, so for example, for my background, I went to the surveys and I talked to the people in WWF or wildlife organizations in my country, and I got opportunities for experiments. So that's one thing. Actually, I'm personally right now I can't recall. So there is another question which is about passive acoustic monitoring for coral reefs. I do know that there are data sets which are using images, and they are using underwater robots and collecting imaging of the coral reefs. But I'm not sure about passive acoustic monitoring. Passive acoustic monitoring might be used for sizing if you use the I mean, if you use the side scan sonar, it's not precisely the passive acoustic monitoring, but side scan sonar can help to map the coral reefs, by the way. So, but if you know any.
Yeah, I happen to know that because my lab in Singapore also dabbles with coral reef acoustics. So in doing that, I have done a little bit of literature review. So I'm just finding all the groups I've been looking at. I will ping some groups in this chat. So there's a question on communicating with the group. So there is an ECOPS group, global ECOPS group. I don't know if I can send an invite to that group, but if Evgenia or Natalie are here, would you be able to send a link to that group? So that's one of the ways to communicate with the group. You can also email directly. And you can check out ecopdecade.org for the ECOP program and details on what the program does and upcoming webinars. So Pratita has her hand up. Pratita, do you want to unmute yourself to ask your question?
Hi. Hello. Prof, I'm from Indonesia, and Indonesia have artisanal fisheries, artisanal fishermen around 90%. 90% of our fishermen is artisanal. It means a traditional and in the coastal line, and something like that. We have no. They using acoustic for fish finder machines, but the price in Indonesia around 55 million. Around $400 US. So I want to ask you, is it possible this technology? Yes, it helped the fishermen, our traditional fishermen, but the other side, it is a little bit expensive for them. So I want to ask that, is it possible that the technology is more cheaper than right now? Is it possible or not? Thank you.
I think, well, it depends, like, the $400 US echo sounder, you can find maybe for even, I think $200 would also be available. But again, those echo sounders are just reasonable enough. I mean, those are not very accurate, by the way. Those, the low cost ones, because they don't do very, great processing or very feature specific processing. Mm-hmm. And the second, I mean, being coming from the environmental side, I would rather add here one thing, that while using the echo sounder, I don't know how do they use in Indonesia, but so normally the focus is on getting more fisheries actually. So, so in order to, I mean, getting a good catch is fine. Like getting a big catch is good, but from my background, I can tell that this technology should be used very prudently. Like you can use echo sounders to catch more fish, but if you do it intelligently, maybe you can catch big fish in less number, but more economically useful. So this is just one point which may not be directly relevant to the answer that you're looking for. Low cost echo sounders possibly are can be made, but I think it's more of economy of scale thing, because normally right now this underwater sonar systems, the main users of these systems are either research groups, some environmental organizations, to some extent fisheries, but still I think it's a small group. That's why as a result of that, you do have some sensors which are around $200 to $400 US range, but those are like not very high quality. Most probably, if you have many people using underwater technologies, so you might have echo sounder as cheap as maybe a microphone or a speaker that you use with the computer, right? but that, that directly relates to the, economy issue. I think because it uses a piezoceramic disc. It's a material which is actually very cheap, but it's the technology and the cost of production which creates this cost issue. Yeah, maybe if Hari wants to add something.
Yeah, thank you, Prof.
Yep. So
another question is, can we predict storms coming in the ocean with sound? I think that's an interesting question.
yeah,
You want to take
I think
it first?
I know. Well, you like sounds, based on the early tsunami systems. If you might have heard, there's an initiative that involves many governments. Like I know about Japan because I have links there, so I know their Jamstack and their organizations. They are contributing to the development of early tsunami systems. So this is a sort of like an ocean-based event which can be detected with an early warning of maybe few seconds perhaps, but again, so yeah, I mean storms can be listened at least, but how early can those be listened, that we can't say. Like, I mean, I would talk about because I have read a little bit more about tsunamis, so that's I'm talking about those events. So we do have triggers based on those early warning systems which tell you about the possibility of a tsunami, and based on that areas are evacuated. But that's not just based on the acoustics. I mean, acoustics is also used, but that also involves satellite imaging that looks at particular environmental parameters affecting the ocean waves at a particular point in space. So such early storm monitoring systems or early warning monitoring system would probably be more multimodal, because sound would listen to something which has already happened, maybe at a far off place. So it can be an early warner based on a few minutes or seconds, but on the order of hours or on the order of days, it might be difficult if you're taking a storm, if you expect to record the signature of a storm using audio or hydrophone directly, because if an event has occurred and it is moving towards you, most probably it will reach very quickly to a particular designated location. So, but if you couple it with prediction models that air movement or underwater acoustic current movements, that you're measuring how far quick underwater currents are moving, and many other environmental factors, coupled with that information, it might be a better early warning system for storms, or maybe more appropriate for tsunamis.
And just to add on to that, so I don't know the exact event, but I do know that one of the recent tsunamis or something, it was, I think, the early warning system in Japan that caught it a few hours before it happened. So a few hours can be very valuable in such systems. So
yeah,
yes, it is possible.
right.
So while we wait for any other questions, I just want to mention that we should be having more similar webinars coming in the future, hopefully on topics such as what kind of underwater technologies are used in polar environments, maybe to study climate change and things like that. We have one coming on underwater robotics. We likely have one on underwater communication coming up. So stay tuned, and hopefully we will see more of you in some of the coming webinars. So I'll wait like a minute more to see if we have any more questions. I'm happy to see that we got many questions, and I hope we didn't miss any. yeah, I don't think we missed any questions there. So. If anybody has questions, this is your turn. This is your chance. Okay, going once, going twice. All right. So thanks once again, Suleman, and thank you everybody for attending, and thanks to the ECOP program for facilitating this and giving us a good platform for this. We hope we can have more such talks in the future, and we hope we can see more of you in some of these talks. Thank you.
Thank you very much. Have a good day.
Have a good